Hi, welcome to the Signal Path. In this episode, we're going to try another repair. This is an Agilent E4448A. It's a PSA series spectrum analyzer, goes all the way up to 50 gigahertz, and it's actually a fairly old unit. It's one of the ones I used during my PhD. Now, I tried to turn this on. It actually did turn on. It booted for a while, and then it shut off. So it may simply have a power supply problem, but it never got into the boot enough for me to see its RF capabilities. And then, you can see that now it doesn't turn on anymore. It sometimes does. There you go. It just did. So I wonder if it's just simply a switch problem. I'm not sure, but nonetheless, we're going to take it apart and find out what's going on with it. It's booting now. Let's see if it turns off. Well, as soon as it got into the main screen before the spectrum was sweeping, it turned off again. You can see the switch is pressed, but it's turned off. And if I do this again, yeah, it doesn't do it. So yeah, maybe, I don't think it's a switch one because I did tap it a few times while it was booting and nothing happened. Nonetheless, it's either the power supply or the switch, or maybe there's something inside of one of the boards that comes online and it shorts the power supply and it causes it to stop working. Well, let's take it apart. And here's the instrument with the top cover off, and we see all the familiar components, some submodules for the triple conversion super heterodyne architecture these instruments have, and we've talked about that in some of the previous videos. So we do have our front-end attenuator, electromechanical, with a front switch that brings in the IF calibration signal in. Our YIG assembly is over here, our main converters, LO distribution over here. Then we have this main board that controls everything in the front end. The next one is the synthesizer assembly, also obviously pretty crucial, providing all the LO signals and working with the YIG in the front end. The reference assembly for the main reference of all the synthesizers. This is the third converter in the super heterodyne chain. This is the second LO, and that component right down there has a history of going bad in various assemblies like this one. We have our analog IF assembly, digital IF assembly, and then the three options which are not populated in this case. And here's the front end switch all the way down there, so it's nice and accessible. You should be able to spray something in there, but I don't think that's the problem. And then of course the main power supply, which is suspect at the moment. So let's take it one step at a time. So even though we don't have the full schematic, there's some useful information in the service manual. So here's the on and off switch. We can zoom in there a little bit more and see that it is indeed simply shorting the switch to ground. And we can follow this line and see where it goes for the power on. And it seems that there are a pair of MOSFETs over here. They're actually in parallel, so it's almost like just a footprint change between the two of them. So what we're doing is that we're simply pulling down the gate of this MOSFET, allowing it to turn off, and therefore the drain will be released, and that will then turn on the other power supply. When the switch is off, this is pulled up to the standby 15-volt power supply. The transistor is turned on, pulling this drain down to ground, and that is what's keeping the power supply turned off. So it's a pretty straightforward thing to try to see if the switch is working or not. So let's go ahead and quickly verify that the front panel switch actually works with the power supply removed. We do see the transistor involved in the power on sequence. So we can go ahead and measure on the one side of the resistor connected to the front panel switch over there. That's on this side, I believe, if I can get the connection. There we go. So right now the switch is turned off, so we're seeing a very large resistance, and we turn the switch on, and it goes to 0. Yeah. Turn it back off, turn it back on, wiggle the switch. Yeah, it's rock solid. So I think I'm reasonably convinced that the front panel switch is definitely working. The problem is from something else. Okay, so I went ahead and I connected this brown cable to the drain of that MOSFET in the power on sequencing transistor there. So right now the instrument is plugged in, and when the instrument is plugged in but not turned on, the gate of that transistor is sitting high. As a result, the drain is being pulled down to ground, and we're reading in fact 0 volts on there. But if I try to turn it on, look what happens. You kind of see it jumps up, but it's only sitting at 1.1 volt. If I turn it back on, it goes back down. So I have a feeling that that transistor isn't really fully turning off, and that perhaps has some leakage to it and is preventing this to turn on. And it's kind of sitting at a border, so sometimes maybe it can turn on, then it heats up and it doesn't allow it to turn on anymore. So I suspect that that might be an issue. We should try and replace that transistor just to make sure. Well, I managed to get the transistor out. Unfortunately, one of the legs broke off from the package because that was the source, and that is on the ground plane of this footprint. And I have to remove this from the top of the PCB, not from the bottom, because removing this entire motherboard will be an absolute pain because you have to remove all the cards to get it out. So I really didn't want to do that. But unfortunately, we can't test this anymore to see if this really was the problem or not. But looking at it closely, you can also see the other footprint. So it can accept a surface mount, which is probably a lot easier to solder back in this case. So we're going to use that footprint. And yeah, we're not going to find out until we replace and see if that does anything at all. So there is nothing particularly special about the transistor that I took out. It's just a normal N-channel transistor with a 60-volt breakdown between the drain to source and a 20-volt breakdown between the gate to source. So I'm sure I can find one in this booklet. We just want something equivalent. And here's a replacement. I also soldered 2 pins so we could monitor the voltages again, just in case we need to take a look because I couldn't clip on anything to the legs anymore. So let's try this out. Well, what do you know? It does exactly the same thing, almost identical. The voltage goes to the same place, and sometimes it boots up and sometimes it doesn't. So now I'm beginning to think that that voltage is actually an intermediate voltage where the power supply is choking, meaning that it tries to power on, it can't, and it basically is hanging somewhere in the middle, still in standby. I believe that's what's going on. So something maybe is loading the power supply during power on or at some random time, causing it to overload and shut down. So now we have to really dig into the rest of the system, and one quick way to find out is just unplug one thing at a time and see at what point it reaches the complete boot system, and then perhaps that can point us into one of the assemblies. Now there was one other thing I did to try and convince myself that the power on sequencing wasn't the issue. I actually overrode that voltage using an external power supply, and I forced the power supply to try and stay on, and it still did the same thing. So it has nothing to do with that part of the circuitry, it's just simply being loaded down. And I started disconnecting one assembly at a time, and what do you know, it was the last thing I tried that actually made any difference. So I simply pulled these out away from the motherboard, disconnecting them, so they would no longer power on. Now the system would still boot because these RF assemblies have nothing to do with the CPU that runs the operating system. And it worked all the way until I reached this last one. Then I started unplugging each of the ribbon cables that control various aspects of the RF front-end deck. And when I disconnected this cable, it did boot, and it booted consistently. Now this cable goes into a little board down here, which is a power supply board that powers several of the different modules in here, including the LO distribution, the YIG preselectors, and so on. So now I started disconnecting those one at a time, and this was the culprit. If I were to disconnect the dual YIG preselectors that are on top of each other, which are driven by this cable, it actually consistently boots. Now it may be that there's a problem in here, or maybe there's a problem in this motherboard over here. Now these YIG preselectors are going to have pretty high currents through their coils, and we'll talk about that in detail in a second. So it could be that either the coil is damaged or the driving circuitry is damaged, or maybe something similar to that. So let's take it one step at a time. And here's a part of the block diagram of the entire instrument. There are so many cool things here we can talk about and dig into it depending on if we find anything else wrong with the instrument. But the part of the unit that appears to be preventing it from powering on is this assembly A19, which is a pretty important component. But it also has 2 YIG preselectors on them. One over here, one over here. One of them covers the millimeter wave band above 26.5 gigahertz. One of them what they call the high band from 2.85 to 26.8. And there are various switches in there that reroute the signal and LO coming in and out of it, so it's pretty important. Now these YIGs are fairly high power devices because of the magnets required to run them, and that might be partially responsible. But we won't know until we take it out of the unit, which is going to be a lot of work. So in order to take this assembly out, you have to take the entire RF front-end deck out and then slowly remove everything, and all the rigid coaxes need to come off for this piece to come out. So it takes quite a lot of time. And I actually discovered something interesting on it. Someone has already repaired this, and you can see that it says it's been repaired not too long ago, January 11, 2024. So someone's worked on this, and I could kind of tell as I was taking it apart because none of these coaxial cables were properly tightened back in place, which is not a good sign, because if you don't tighten them back in place, the performance of the instrument will be degraded, and also the uncertainty of the instrument will be quite significantly affected. And then I started looking around a little bit more, and if you look over here at the 2 coils that drive the YIG centers, look, this wire is really, really close to the body. Now I wonder if that has something to do with the short we're seeing or the intermittent distinct powering on and off. It's really, really close. Now these coils should measure about 30 or 40 or maybe 50 ohms depending on the coil. So we can measure those and see if there's any connection or if it's really close to connected to the body. Unfortunately, I've handled this already, so if it was very close and touching, I may have moved it, but we should get some information anyway. Okay, let's quickly measure these coils. So here's the coil from the bottom YIG. There you go, 29 ohms. And we can measure that coil with respect to the body. There should be nothing. There you go, this is nothing, and of course this one's going to be nothing. Now for this one, we can do the same thing. Measure between the 2 of them. 21 ohm, okay, not too bad. And now between this and the body. Oh, look at that, 27 ohm. So between this and the body is a short circuit. Yeah, that's what I thought. This is really close. Now I wonder if this is the only issue. I guess one way to find out is to just move this around a little bit, put some insulation around it so it never shorts again, and then try again. No matter what, this is not a good condition anyway. Unfortunately, there's quite a bit of things to put back together before we can test it, but hey, this is a good sign. If I push down, yeah, you can see that resistance is intermittent. That at least tracks with the behavior of the power supply. Okay, I went ahead and reassembled everything. Now, if I had just looked through this gap, which is hard to see on camera, but the cables that were really close to the body were kind of visible from there. So I might have been able to notice that there was something, although it was the bottom one of these two stacked devices. So maybe from the corner here, you could have seen something. But hey, I still had to take the whole thing apart and put it back together. But at least now all the coaxes and everything is nice and tightly coupled. Okay, everything's back together. I haven't put the cover back on the power supply. I will definitely do that. Let's try this out now. We're going to do this at the same time. And aha, turns on. Well, that still doesn't mean much because it did used to turn on occasionally and it would just turn off before it completely boots. So let's see how it behaves after a few minutes. Check it out. This is the first time I have seen the instrument reach this point where it is doing all of its internal alignment, and hopefully it doesn't generate any other errors and there's nothing else wrong with it, but then we should see a full trace. We will still have to, of course, test it between DC to 50 gigahertz to make sure it does work because all the YIG stuff can be quite suspect. But let's see what happens. Well, after the booting, we do have one error, and that is the attenuation steps error. This is quite a common failure for these spectrum analyzers, especially if they're older, because of the electromechanical attenuators eventually failing due to the many strikes and several other problems they can develop. We can certainly measure this. This is actually not one of the worst things that could have been wrong with the instrument after everything we did to it, but let's see what's wrong with the attenuators. Now, there's a fairly simple way to quickly check the attenuation to see if it makes any sense. What we can do is we can enable the internal 50 megahertz alignment signal, which can easily be enabled by just putting it up here. So now we have a 50 megahertz that the instrument is internally generating, and I have already set the front-end attenuation to basically 0 dB. And what this will do is that it will measure that amplitude directly, and that amplitude should be around minus 25 dBm. At the very, very top of the screen, you can see that it says minus 25 dBm. Now, if I increase the attenuation, the value should not change because the instrument automatically corrects for that. The noise floor will go up, but the amplitude should remain the same because it's corrected. We can go up 2 dB at a time and see what happens. So if I press this, there you go. You see after 2 dB of attenuation, nothing is wrong. We can keep going. Still looks good. Still looks good. So 10 dB attenuation is okay. 12, 16 is still okay. 18 is still okay. Oh, did you see that? That was a problem. So the 20 is struck once and then now it's measuring the wrong value. So the 20 dB attenuation path is bad. 22 is okay, 24, 26. Now as soon as I hit 30, oh, it's completely gone. That is really bad. Okay, so the attenuation is pretty bad. Okay, doesn't work, and the 40 doesn't seem to work. Okay, so we do seem to have a problem. Certainly, going back down here, and it starts showing up around here again. Yeah, okay, so the attenuation is bad. Let's take a look at the attenuator a little bit more closely. Now, looking at the front end of the instrument's attenuator, we can see where we need to pay attention to. So this is where the 50 megahertz calibration signal enters the instrument. There is a total of 10 dB attenuation in this front end switch, so that's how we get the fine 2 dB step control. And then there is the big attenuator, the 10, 30, and 20 dB pads, which we will have to take a look at and debug. So let's take this out and measure it separately. So let's go ahead and use the Keysight Field Fox, which is a 50 gigahertz instrument, and we're going to measure this attenuator across this entire frequency band. Now, we saw from the block diagram that this attenuator really only has 3 sections in it, a 10 dB, a 20 dB, and a 30 dB pad. Should be pretty easy to measure. Now, if all those pads are disabled, you basically have a through, and that through has a certain loss. It's not that much. You can see here at 25 gigahertz is only about 1 dB. I'll zoom into the screen. But we can go through the attenuation steps and actually see this attenuation change step by step, and we can see what's wrong with each of those individual ones and what has happened to them potentially. So let's take a look. Okay, so with 0 dB attenuation, we have a nice flat line. We can see about 0.8, 0.9 dB of loss at 25 gigahertz. So things are looking good. So the through pad is definitely working when all the pads are not selected. Let's go and add 10 dB of attenuation. And here's 10 dB, and the 10 dB attenuation also looks good. Again, completely flat. We added essentially exactly 10 dB to this value. It's a nice 50 gigahertz attenuator. So far, so good. Now let's try the 20 dB pad. And look at that. That is a very interesting piece of information. This tells us that the low frequency isn't working. And that's probably because there is no good contact on those attenuator paths, because this is electromechanical. So because it's not making good contact, the low frequency immediately drops off, because basically we are capacitively coupled at that point. This is a very common issue. And it gets very flat at higher frequencies, so it would have no problem working at higher frequency. But the training signal, the alignment signal of the instrument, is at 50 megahertz, which is landing somewhere around here, and of course it's not going to work, and therefore we're getting this error. Let's see if the 30 dB pad works. There you go, the 30 dB pad has a similar problem, and if I go to 40, yeah, it's just going to keep going down because the problem is just compounded. There you go, look at that. And then we run into some dynamic range issues. Yeah, so I think we understand at least what's wrong with it in theory. Now whether that's fixable or not, we're going to open the attenuator and find out. And here we are looking at the top of the attenuator, seeing all of its internal constructions, which is fairly interesting. So this is the connector on one side. So if I scroll over here, you can see this is one of the connectors, and all the way on the other side is the other connector. Now this only has 3 sections, so we expect to find 3 attenuator pads, and they're upside down. And here's one right here. So this wiper here goes up and down. At the bottom, it touches a through, and at the top, it touches the 2 sides of this attenuator pad. And that's how it works, and I've described that previously on the channel. So if I press over here gently, you can see that this goes down like so, and there's a piston in here, and that piston, by moving up and down, bends this in a certain way, allowing it to connect to the bottom or connect to the top. And there's one on this side and there's one on this side. Now we should be able to very carefully remove this. So here's the ground connection. We don't really need that for our purposes, and this is not the issue anyway, so we put that up here, and there's another one over here. You can grab that. These are pretty small, and we can put that over here as well, like so. I have to make sure that I don't install it upside down. Now we should be able to remove this attenuator pad very carefully, like so. If I can get my tweezer in there. Oh, this is really stuck in there, so I have to work at it a little bit carefully. It's difficult to look at the screen at the same time. There we go. It came out, and it jumped somewhere. Here is the attenuator there. So it's still upside down. I can flip it the other way, and we can look at the top side of it. And here's the top side. Now if you look carefully, you can see where the strike places are. So right over here and right over here is where those 2 pads are actually striking this. So by removing it, and by the way, the through is at the bottom. You can see the through. So when it's all the way at the bottom like this, it touches the through. So I'm going to go ahead and gently clean this, very carefully, gently clean these, and just moving it around will change the places it is striking. So that will be quite helpful. There's obviously a lot to worry about. I've done this already with this one. You can see the other attenuator. You can see it looks different because it's a different attenuation level, and there's one more all the way at the end. So I will do exactly this, keeping the order where they belong, and do this cleaning and put it back together. Okay, the individual attenuator pads have been somewhat cleaned. You can't be too aggressive with these because otherwise the attenuation will change and the whole thing falls apart. We know we're dealing with a contact problem, so we may have to do it more than once, but let's take it gently. And on the attenuator side, I have lowered the pistons. So you can see the pistons are at the bottom. This makes it a lot easier to put the attenuators back on. Otherwise, they'll be constantly being pressed down from the bottom, which is not a very good situation. And I've done the same thing for all of them. I also cleaned the contacts again very gently. And then now we can put the attenuators back. And here's one of the attenuators put back. You can see that the ground connections are in the correct orientation, pointing down. Everything looks good so far. Another interesting thing to pay attention to is the lid that goes over the entire structure, over the entire top that you were just looking at. And this has a few interesting things in it too. First, it has RF absorbers to avoid any cavity modes, any other unusual coupling that can happen. This absorbs all of that. There's some gaskets over here and here, making a nice good RF seal. And then there are these screws. There's one here, and one here. These sit at the top of the attenuators. They don't touch them, but they hover over them. And you can see that they have been lowered in different amounts. And this is adjusted at the time of factory. And this is basically tuning, because by bringing these screws close to that, you create some capacitance, and that capacitance can interact with the rest of the EM model of the entire structure to create a nice flat response as much as possible. It's almost like a little filter design, just to make the entire frequency response flat. I think that's what they're for. I haven't noticed this at lower frequencies, but at such a high frequency, everything matters. All the little inductances and anything that shows up matter, and you really want a flat response. And we saw that the response was nice and quite flat across the entire band when it was working, except for the low frequency contact. So let's put it back together and see if we have made any difference. Okay, let's give it one more try. I closed it up until a point where I can measure it. There's no reason to put the casing on, because if it hasn't been fixed, we have to do it again. Let's take a look. Okay, so here we are at the 0 dB attenuation state, and you can see we have about the same attenuation we had before, so that's good. Nothing's changed significantly, and we haven't damaged anything. Let's go 10 dB attenuation. Look at that, 10 dB works good, but 10 dB was working before as well. Let's try 20. Aha, look at that. That looks great. There is no drop here anymore, so that looks good. Let's try 30. And 30 looks good. That's a huge sign. Let's go more now. Now 40 is just going to be an addition of 2, 50, 60, 70, and now I think we're getting below the noise. Yes, but 70 needs the internal additional 10 dB. So yeah, it's working. That is pretty sweet. All right, well, let's put the whole thing back together. Let's see if the alignment errors have gone away. Well, the good news is all the errors during the alignment are all gone. And you can see we're measuring here signal at 2 gigahertz with the correct power and everything. But the bad news is there's still some bands don't work. You can see that the signal disappears around 3 gigahertz and it comes back again later at some point in the later frequency ranges, like something over here. So this is most likely because of how this front-end YIG is working and the different bands are not switching, or some of the mixers may not be working. So whoever did that repair may not actually have done a really good job on that. But I think I'm going to stop here so we can create a second part in this video, because this is going to require a lot more investigation. Let me know what you think in the comment section if you have any suggestion. As always, you can support the channel with Patreon or PayPal. It really helps a lot. I'll see you next time. And Pooch approves. Pooch, do you think we should make a part 2? Of course.